Very good evening, sir.
Am I audible?
Yes, sir, audible, sir.
Okay, great.
A warm welcome and very good evening, all dear participants. A resource person of today's session, our respected Dr. Indranil Saha, sir, and chairperson of today's session, Dr. H.S. Mishra, sir. Now, I would like to introduce today's resource person of the session, Dr. Indranil Saha, sir. Sir is currently serving as a scientist E, Center on Non-Communicable Disease, ICMR. Sir has been served as an assistant professor at Burdua Medical College and associate professor at IQ City Medical College, Durgapur, and ESI, PGIMSR, and ESIC Medical College, Joka, Kolkata. Sir is a member of Medical Education Unit, Curriculum Committee of IQ City Medical College. Sir is a fellow of Indian Public Health Associations. Uh, he has judged as Best ICMR STS Project in 2016 and Guide of PhD thesis. Sir is working as a managing editor of Indian Journal of Public Health, PubMed, 2019 to 2021, and as a editorial board member of Indian Journal of Community Medicine, PubMed, 2018 to 2019, and as a national advisory general board member of Medical Journal of D.Y. Patil Vidyapeeth since 2016. Sir is selected as a one of the top 1% of peer reviewer in 2017, 18, 19, Medicine and Allied by Babylon's reviewer of national and international journals, Bulletin of WHO, Indian Journal of Community Health. Sir has published some important books like Essential of Biostatics and Research Methodology and Textbook of Preventive and Social Medicine, Mahajan and Gupta. And beside that, sir, I published a book chapter on Gautam Ghosh, Indranil Saha, sir, food safety during fairs and festivals, chapter 33 in food safety in the 21st century, public health perspective, academics press, L. Schreiber publication 2016. Now, I would like to request sir to kindly lead today's session. Please, sir, welcome, sir.
Okay, thank you, Tiwari ji. So, for the warm welcome message. So, should I now start?
Yes, sir. Yes, sir. Our respected chairperson is still trying to connect with us. There is some network issue. As soon as he connect, then
Then,
I will announce them again. So
then,
please,
then,
please,
then,
please
then
proceed.
should then should I start?
Yes, sir. Please, sir. Welcome, sir.
Okay. So, with your permission, I'm sharing my screen. Is my screen visible to all of you?
Yes, sir. Visible now.
Great. It is now full screen, na?
Yes, sir. Perfect, sir. Perfect, sir. Thank you, sir.
Great. So, without wasting time, so I'm starting today's session on fundamentals of testing of hypothesis. So, whenever we talk about the data, we basically deal with two types of data. One is the qualitative data, and one other is the quantitative data. I think all of you are aware of these terms. So, one is the qualitative data, and one is the quantitative data. So, when we are dealing with the qualitative data, then we present the data in terms of number and percentages. So, this is the only option what we have. So, when we are having qualitative data, the only option is to present them in number and percentages. But when we are having quantitative data, then at first we have to see whether the data set are normally distributed or not. So what we say, whether the data set are normally distributed or not. So in presence of normal distribution, we present the quantitative data in terms of mean and standard deviation. But when we see that the quantitative data are not normally distributed, that is known as the skewed distribution. In those situations, we don't go for mean and standard deviation, but in those situations, we go for the median and interquartile range. So please remember, in presence of skewed distribution, we present the data in terms of median and interquartile range. The same is being also applicable when we are also having outlier in the data set. So in presence of an outlier, we present the data in terms of median and interquartile length. So please remember, this is the basic fundamentals of presentation of data. So qualitative data, number and percentages, and quantitative data in presence of normal distribution, we have to present by mean and standard deviation, and in presence of the outlier or in presence of the skewed distribution, we present the data by the median and interquartile range. So that is the simple example we see. Say for example, in today's session, there are 108 participants. So according to the number of participants according to the gender, I have distributed. So sex is an example of the qualitative data. So gender is an example of qualitative data. So I've distributed the entire class in terms of the gender. How many participants are male? How many participants are female? So in that situation, I have presented it in by number and followed by percentages. But say for example, if I ask you a separate question, what is the distribution of the weight of the male and female participants in the class? So weight, as you understand, weight is a quantitative variable. So in case of the quantitative variable, we checked that the weight is normally distributed. Please don't worry about normally distribution. I will show you in SPSS how do we see whether a data set is normally distributed or not. So since we have, say for example, you understand that we have seen that weight is normally distributed. So in this situation, what I've done, so the male, the weight, you see I have presented it mean and standard deviation. In case of female also, mean, weight and the standard deviation. So in presence of normally distributed quantitative data, that is weight, I have presented the data in terms of mean and standard deviation. So you see the mean weight of the male participant was 72 kgs with standard deviation 10.85, and the mean weight of the female participants is the 68.36 kg with a standard deviation of 12.52. So this is the basic step that you have to understand. Now regarding the test of significance, as you say that there are two types of test of significance. One is said to be the parametric test, and another type of test, these are known as the non-parametric test. So what is parametric test? Parametric tests, these are only applicable in presence of continuous or quantitative data. So please remember, this is very important. So parametric statistical tests are only applicable in presence of continuous or quantitative data when data set are distributed normally. But in contrast, non-parametric statistical tests are applicable in presence of qualitative data. So non-parametric is applicable for qualitative data. In addition, it is also applicable for the quantitative data. But when the data set is not normally distributed. So when we say when the data set is not normally distributed, what does it mean? It means that it is either having skewed distribution or it is containing some outlier. So please remember, this is the basic thing that you have to remember. So tests of significance, it may be either parametric or it may be non-parametric. So parametric tests are applicable for continuous or quantitative data, provided data set distributed normally. In contrast, non-parametric tests are applicable for qualitative data as well as for the quantitative data when the data set are skewed or having the outlier. So this is the list of the different parametric tests and the non-parametric tests. So you see, we in this today's session is a very small session. I will try to explain all the tests and when it is applicable. So application of the different types of tests, I will try to explain to you. So this is the list of the parametric test and this is the list of the non-parametric test, corresponding non-parametric test. So if you see the most common non-parametric test, that is the chi-square test. This is the test that is only applicable for qualitative data. There is no such parametric counterpart of this test for the qualitative data. Now you see, all of us know that unpaired student t-test, its non-parametric counterpart is the Mann-Whitney test. There is another test, paired student t-test, its non-parametric counterpart is the Wilcoxon-Matchett pair test. So one way ANOVA, its non-parametric counterpart is the Kruskal-Wallis test. Repeated measure ANOVA, its non-parametric counterpart is the Friedman's ANOVA. Pearson's correlation coefficient, its non-parametric counterpart is the Spearman's correlation coefficient. So linear regression, its non-parametric counterpart is the logistic regression. So all these tests I will try to explain before you regarding their applications. Now again, I'm coming to the same topic again. So when we are having continuous or quantitative data, often we do wrong thing. Whenever we see continuous or quantitative data, we present it by mean and standard deviation. So this is wrong. What I've already explained to you. So please remember, whenever we are having continuous or quantitative data set, first of all we have to see whether the data set are normally distributed or not. So this is like a picture of normally distribution, where mean value and mode value, all of them they coincide with a single value. So in those situations we go for the parametric test. But when we are having skewed distribution, this is an example of right-sided skewness because tail is on the right-hand side, and this is an example of the left-sided skewness because the tail is on the left-hand side. In those situations, in presence of quantitative data, we go for the non-parametric test. So please remember, these are the applications of parametric and non-parametric tests in presence of quantitative data. But again, as I have told you, always go for non-parametric test when we are having qualitative data. I think that up to this much it is clear to all of you. Now, I'm repeatedly telling that we have to see whether the data set are normally distributed or not. Now I will show you how to test the presence of normal distribution in a data set. These are the different statistics that we commonly do to test to see whether a data set is normally distributed or not. So one of them is the skewness and kurtosis. Second one is the Kolmogorov-Smirnov test. Third one is the Shapiro test. Fourth one is the histogram, and fifth one is the quantile plot. So these are the different options what we have to see whether a data set is normally distributed or not. But most commonly, please remember, most commonly we go for this test, that is the Kolmogorov-Smirnov test. So please remember, most commonly we do the Kolmogorov-Smirnov test. What is the interpretation? When we get a non-significant p-value, when you get a non-significant p-value, what does it mean? P-value more than 0.05, that will only indicate the data set is normally distributed. So in Kolmogorov-Smirnov test, if I see the p-value more than 0.05, that is not significant, that indicates it is normally distributed. But if the p-value is found to be less than 0.05, that is statistically significant, then it indicates it is not normally distributed, rather it is having skewed distribution. Am I clear? So please remember, this is very important. So in Kolmogorov-Smirnov test, I will show you how to do the Kolmogorov-Smirnov test. In this test, if I get the p-value more than 0.05, that is not significant, that will indicate normality. Less than 0.05, that will indicate significance, and that will indicate the data set is skewed distribution. So this is the an SPSS software I'm showing you. Suppose in the first column we are having the age of the different participants. We have to click analyze. Once we have clicked analyze, a drop down menu will come down. We have to go for the descriptive statistics. Now once you have brought your cursor in the descriptive statistics, then another window will come up having frequencies, descriptives, explore, all these things. Now you have to click this explore. So am I clear? So in the SPSS, you have to click analyze, you have to click descriptive statistics, you have to click explore. Once you have clicked the explore, this box will come up. So in this box, age will come up here. So now by clicking this button, age will be shifted from this box to this box. Then you have to click plots. Now once you have clicked plots, this another box will come up. By default, you will see normality plot with test. This is not selected. By default, it is not selected. Then you have to click this one. You have to click this one and you have to click continue. Now, once you have this continue, then you will see the test of normality is given. So Kolmogorov-Smirnov test, you see, this is the statistics, this is the DF value, and this is the significance. What does it mean? P value is less than 0.05. What does it mean? P-value is statistically significant. What does it mean? Since p-value is statistically significant, we will say the data set is skewed distribution or it is containing an outlier. It is not normally distributed. The same interpretation is also being true regarding the Shapiro-Wilk W test, where you see the p-value is the significant. So when p-value is less than 0.05, then only we comment that yes, the data set are not normally distributed, rather it is having skewed distribution. Am I clear? This is how we do the test of normality. Next, what is the how the different statistical test appears? So as a medical researcher, as a medical scientist, how will you do, how will you select the different statistical tests? That I am giving you the impression in this slide. Say for example, we are having two groups. Say for example, we are having first year medical students, first year medical students. Say for example, there are section A and there is section B. So first year medical students, they are divided into section A and section B. So how many groups? Two groups, section A and section B. Now we have checked the weight of all the students of section A, and we have also checked all the weight of students of section B. In that way, I have checked the mean weight of section A, and I have also checked the mean weight of the section B. Now I want to compare between section A mean weight versus section B mean weight. Again, I'm telling you, you might ask me, sir, why did you calculate mean and standard deviation of section A and section B? Then my answer is, I have checked normality distribution by Kolmogorov-Smirnov test, and I have seen that this weight is normally distributed. So that is why I have calculated mean of these two sections. So between these two groups, which statistical test is applicable? The only statistical test that is applicable in this situation is the student's t-test. It also known as the t-test. Why this test is known as the student t-test? It is named after William S. Gossett. He is an English statistician. During his PhD tenureship, he introduced all the statistical tests, and he published all the statistical tests in a big journal, statistical journal, under using this name pseudonym student, so that nobody will be able to identify him. So that is why this test is named as student t-test by William S. Gossett. This student t-test is further divided into two types. One is the unpaired t-test and second one is the paired t-test. What is unpaired t-test? When we try to compare between section A versus section B, two independent sample, mean weight of section A versus mean weight of section B. In this situation, we go for the unpaired student t-test. But when we go for the paired t-test, say for example, in section A, I have seen the mean weight of the first year medical students of section A. Say for example, it is 90 kgs. Now my principal is worried, okay, the mean weight is too much. So many students are overweight, so many students are obese. So you do something. So I have devised some intervention like activity, physical activity, as well as the dietary practice as well. And then in the same section A, I have implemented the same exercise and dietary habits for continuous 6 months. After 6 months, I have again taken all the students' weight and I have again calculated the mean weight. Say for example, as on today, that is 14th March 2023, the mean weight of section A student is 90 kgs. Next 6 months, I have given some exercise. Say for example, after 6 months, I have again measured their weight and I have calculated the mean weight. So in the month of September, say for example, the mean weight has come down from 90 kgs to 86 kgs. Now I am interested to know whether this decline is statistically significant or not. So which statistical test will be employed here? Here we will employ the paired t-test. So single sample before and after an intervention. So I think it is clear to all of you, when we are having two groups, the only test that is having student t-test for quantitative data, provided data set are normally distributed. When we are having two different samples, then we go for the unpaired t-test. When we are having same sample before and after an intervention, then we go for the paired t-test. All these things are applicable provided data set are normally distributed. Say for example, I am having the same situation, section A and section B, but unfortunately, weight is not normally distributed. Weight is skewed distribution. So in this situation, instead of unpaired t-test, we have to employ Mann-Whitney U-test. So please, the situation is similar. Here also I am interested to compare between section A weight versus section B weight. But since weight is not normally distributed, now here we have calculated median weight and interquartile range. So I did not calculate mean weight and standard deviation. Rather, I have calculated median weight and the interquartile range. So unpaired student t-test will be replaced by the Mann-Whitney u-test. Same thing. Think about the section A. Section A, the mean weight was 90, and again after 6 months, mean weight has come down to 86. But I have seen the weight is not normally distributed. Now what to do? So in those situations, I cannot calculate mean and standard deviation. Rather, we have to go for the median and interquartile range. So now we have to see whether the decline is statistically significant or not. So in this situation, instead of paired student t-test, we have to go for the Wilcoxon matched pair test. So single sample before and after an intervention. I think I am clear to all of you. Now, when we are having more than two groups, say for example, you think about section A, section B, and another section, section C. Now I have seen the mean weight of section A versus mean weight of section B versus mean weight of section C. Now I want to see whether the differences are statistically significant or not. Now again, whenever we are having quantitative data, please remember at first we have to check whether the data set are normally distributed or not. I am telling you this term repeatedly. So once I have checked that the data set are normally distributed, then I have to go for the one way or n way ANOVA. This is one situation when we are interested to see section A versus section B versus section C. So this is the situation where we will apply one way or n way ANOVA test. And another statistical test, that is the repeated measure ANOVA. What does it mean? Think about the section A in my previous discussion. So what is section A? In section A, I have seen the mean weight as on today is 90 kg. After 6 months, the mean weight has come down to 86 kg. Say for example, after 6 months, the mean weight has come down from 86 to 80 kgs. So 90 kgs come down to 86 kgs, then it has further come down to 80 kgs. So three readings of section A. So in this situation, we will apply for repeated measure ANOVA provided data set are normally distributed. But think about the same situation. But if we see that data set are not normally distributed, then what is to be done? Then Kruskal-Wallis H test should be employed instead of one way ANOVA. Same situation, section A weight versus section B weight versus section C weight. But since weight is not normally distributed, we have calculated median weight, and for to compare the median weight, we have employed Kruskal-Wallis H test. And when we are having same situation, section A as on today, section A after 6 months, again section A after 12 months. So three different readings of same group. But since weight is not normally distributed, in this situation, repeated measure ANOVA cannot be calculated. Rather, we have to calculate the Friedman's ANOVA. So single sample over the period of time. Am I clear to all of you? So these are all the different statistical tests that are applicable between two groups and more than two groups, provided we are having the quantitative data. And if we are having normally distribution, then different set of statistical tests. When we are having skewed distribution, then different sets of statistical tests. Now I will give you some examples by means of which you will be more comfortable and more acquainted with the different statistical tests. Now you see, I am giving you one example. An investigator wants to study the association between maternal intake of iron supplements, yes or no, and birth weight of newborn babies. What does it mean? We have selected, say for example, we have selected 200 pregnant women. We have selected 200 pregnant women. Out of these 200 pregnant women, say for example, I have identified 100 pregnant women, those who have taken iron folic acid tablets throughout the throughout the approved period of pregnancy. Whenever they have prescribed, all of them have taken iron folic acid supplementation. So I have identified 100 mothers. Again, simultaneously, I have also identified another 100 mothers, those who did not take iron folic acid tablet. So what I did, after the delivery is over, the mothers, those who have taken iron supplementation, I have taken the birth weight of their babies, and accordingly I have calculated the central measures. Now, can anybody tell me why I have calculated mean and standard deviation here? Because because birth weight is distributed normally. I have seen by Kolmogorov-Smirnov test. So since I have checked birth weight is distributed normally, and I have seen the birth weight of the mothers, those who have taken, that is 3.11, and those who did not take, that is 2.76. Which statistical tests are applicable here? Two different groups of mothers. Birth weight is distributed normally. So please remember, here is the application of the unpaired student t-test. Am I clear? Now say for example, if the birth weight is not distributed normally, say for example I have checked and I have seen the birth weight is distributed skewed. So what I have done, you see, instead of I have created the same table, but instead of mean and standard deviation, I have calculated median and interquartile range. Since the birth weight is not normally distributed, now which statistical test will be applicable? Now unpaired student t-test is not applicable, but its counterpart, that is the Mann-Whitney u-test, is applicable in this situation. Am I clear to all of you? Next, the mean blood pressure of a group of person was determined before and after of an intervention trial. Now you see, suppose there are 500 participants. I have measured all of their blood pressure, and I have seen whether the blood pressure is normally distributed or not. I have seen in SPSS software by Kolmogorov-Smirnov test that the blood pressure is normally distributed. So I have calculated the mean systolic blood pressure as well as its standard deviation at the very beginning. Then all of them were prescribed one antihypertensive medicine. All of them, they continued with this antihypertensive medicine. After 6 months, from the same group again, I have calculated the mean systolic blood pressure. Why? Because at that time also, the mean systolic blood pressure was found to be normally distributed. So same group, before intervention, after intervention, two groups. Which statistical test is applicable here? It is the paired student t-test. Now is it clear? Now say for example, the blood pressure is not normally distributed, blood pressure is skewed. So now what option we have? We have calculated median and interquartile range. Now which statistical test will be applicable here? Same group, before and after. We have calculated median. So paired t-test cannot be applicable here. So instead of paired t-test, we have to go for the Wilcoxon matched paired test. Is it clear to all of you? So these are the different statistical tests between the two groups. I'm not telling this one. You see, this is the another situation where we are having three groups. Now you see, we have selected some of the participants and we have categorized all the participants into three different groups. One is having normal BMI, one is having overweight, one is having the obese. Now we have taken their cholesterol level. We have checked the cholesterol level in the Kolmogorov-Smirnov test. We have seen that cholesterol level is distributed normally. So now we have calculated the mean cholesterol level of normal, overweight, and obese. You see, there are three different readings in three different groups. My intention is to see whether this difference is statistically significant or not. Which statistical test will be applicable here? So please remember, one way ANOVA will be applicable here. More than two groups, quantitative data, and the quantitative data is normally distributed. Had it been so, the cholesterol level is not distributed normally. The cholesterol level is skewedly distributed. Now in this situation, Naturally, we cannot go for mean standard deviation. That is why I have changed it as a median and interquartile range. Now, in that way, I have categorized into three different groups. Same thing. Instead of mean standard deviation, I have calculated median and IQR. Which statistical test will be applicable here? Instead of one-way ANOVA, we will calculate the Kruskal-Wallis H test. So this is the test when you will apply the test. Am I clear? So these are the basic assumptions between all these tests. Now again, I am telling you another story. After prescribing rosuvastatin to reduce blood cholesterol, you see this is the blood cholesterol level at the very beginning. This is the same blood cholesterol level after 6 months. Same blood cholesterol level after a period of 12 months. So group of person, say for example 200 participants, we have taken their cholesterol, we have calculated the mean cholesterol. Why I have taken mean cholesterol? Again same thing, cholesterol was distributed normally. And we have seen that the cholesterol level was pretty high. We advise them to take some anti-cholesterol medicine. They took. Again, I have seen that cholesterol level is again normally distributed after 6 months. We have calculated again mean and SD. Again, I see it is, since it has been lowered, but still it is something high. Again, we have continued our another 6 months therapy. Then after 6 months, again we have seen it has come down to 182. Again, it has come down. So one single group at 3 different times, readings at 3 different times, at beginning, at 6 months, after 12 months, and cholesterol level is normally distributed. So this is the situation where we will go for the repeated measure ANOVA. Am I clear? So repeated measure ANOVA. But if the cholesterol level is not distributed normally, then we have to calculate median and interquartile range. Same situation at beginning, at 6 months, at 12 months. But instead of repeated measure ANOVA, we have to go for the Friedman's ANOVA. This is the non-parametric, this Friedman's ANOVA is the non-parametric counterpart of the repeated measure ANOVA. So these are the different situations and applications of assumptions where different statistical tests for quantitative data are being employed at different situations and different assumptions. So unpaired t-test and paired t-test compares mean values between the two groups. Unpaired t-test and paired t-test compares mean values between the two groups. Unpaired t-test compares between two independent groups, but paired t compares between two related groups, same group, before intervention and after intervention. When we talk about the Mann-Whitney U-test, this is basically the non-parametric counterpart of the unpaired t-test. It compares overall distribution of the values of the two groups. I've told you we generally calculate median and then we use the test and we interpret the test statistics. But we interpret the test statistics not in terms of median, rather we interpret in the terms of overall distribution of values. And the third one is the Wilcoxon matched pair test, compares the median of the two groups. This Wilcoxon matched pair test, this is the non-parametric counterpart of the pair t test between the two groups. Here we compare between the two median values. Now all the different statistical tests related with quantitative data I have covered with the basic assumptions and the fundamentals. Now I am coming to the another statistical test that is known as the chi-square test. This is one of the most commonly employed non-parametric test used for the qualitative data or discrete data. What is said that data must be mutually exclusive. What does it mean? Mutually exclusive means when I have counted one person in one cell, he or she will no longer be compared in another cell. So this is the meaning of the mutually exclusive. Another example, say for example, I'm doing a toss with my coin. The answer will be either head or either tail. So if head is there, then it excludes the possibility of the tail. If tail is there, then it excludes the possibility of the head. So this is known as the mutually exclusive values. So please remember, only actual counts of the variables can be used in the chi-square test. Whenever we do the chi-square test, we create one table like this. This table is known as the contingency table. This is one of the very clear and simple example where I have taken 770 participants. Out of them, 610 participants they received drug A, and 160 participants they received drug B. I've seen out of 600 participants, 510 patients cured, 100 patients not cured, and 160 patients, 110 cured, and 50 not cured. This is the classical situation. You see number of person, number of person. There is no idea of coming quantitative or continuous value like this thing. Nobody will say mean or median like this thing. So here the thing is in how many person, number of persons, isn't it? So that is why I'm telling you that the discrete characteristics, mutually exclusive. Again, the person who is counted in the cured column, she will not be considered in the not cured column. So this is the beauty of the contingency table. You see, this is an example of the contingency table. You see, hypertensive, normotensive, total, education, illiterate, up to standard 10, more than standard 10. So with 1081 participants, they were divided into two groups, hypertensive group and normotensive group, and they have been categorized in presence of the education, illiterate, up to standard 10, more than standard 10. So here we have the classical situation where we will employ for the chi-square statistics. So chi-square test like this thing, we also calculate the degrees of freedom, and accordingly the p-value is calculated. Basically, these are all we feed it in the software, and the software gives it. Degree of freedom is basically calculated by the number of column into minus number of rows. So here total number of columns, you see there might be 4 columns, but actually you see there we are having 2 columns where the body of the data exists, hypertensive and the normative. So how many columns are there? 2 columns are there. How many rows are there? How many rows are there? There are 3 rows, illiterate, up to standard 10, and standard more than standard 10. So in that way, column minus 1, that is 2 minus 1, into row minus 1, that is 3 minus 1. In that way, I have calculated 2, and the software will tell you the whether p-value is statistically significant or not. And we interpret not in terms of number, rather in terms of the percentages. What we see that among the hypertensive, majority were having education more than standard 10. But among the non-hypertensive, majority having the education level up to standard 10. Whether this association is statistically significant or not, that we have calculated by the chi-square test. This was invented by statistician Pearson. So that is why it is also known as the Pearson's chi-square test. There are different varieties of chi-square test, goodness of fit, test of association, or one test of homogeneity, etc. But commonly what we do whenever we are having this type of data, right, we mostly go for to see the association between the two categorical categories. So here two categorical categories are hypertension present or not, and the educational status. Am I clear to all of you? So in these situations we calculate the Pearson's chi-square test, and there are different varieties of Pearson's chi-square test. One of them is known as the Yates corrected chi-square test. This is also known as the continuity correction. This is typically applicable in 2 into 2 contingency table. What does it mean? 2 into 2 means 2 stands for the column and 2 stands for the row. So 2 into 2, regardless of the observed value. This is very important. Now you see in one cell, this cell the observed value is 4. Now we have a caution. Now we have checked what is the expected cell value of this particular cell. Now we have calculated that, and we have seen that expected cell value is 9.86. That is, expected cell value in one of the cell is between 5 to 10. So this is the situation where we will go for the Yates corrected chi-square test. How do we calculate the expected cell value? It is calculated by column total, that is 31, and into row total, that is 344, divided by grand total, that is 1081. So this is the formula by means of which we calculate the expected cell value. So once we have seen in 2 into 2 cell that expected cell value in one of the cell is between 5 to 10, there we go for the Yates corrected factor. You won't face any problem because you have to give command to the software and software will give you so many options. Do you want uncorrected Pearsons? Do you want Yates corrected Pearson? You want Fisher exact Pearson? But it is up to you. You have to decide what one you will select, what one you will take from the output. So this output is generally depends upon the expected cell value for 2 into 2 cell. So 2 into 2 contingency cell, if expected cell value is 5 to 10, we go for the Yates corrected chi-square table. Now another situation you see, this is known as the Fisher exact test. Same thing, 2 into 2 contingency table. So means 2 columns, 2 rows. But here expected cell value is less than 5. What I told you in the earlier slide, it is expected cell value between 5 to 10. But here it is expected cell value less than 5. In this situation, the software directly calculates the p-value instead of calculating the test statistics. Now you see in this cell the observed value is 1. Please remember, we do not comment on the observed value. Rather we take the observed values to calculate the expected cell value. How? You see, for this cell the column total is 31 and for this cell the row total is 63. So 31 into 63 divided by grand total, that is 1081. So in this way we have calculated the Fisher exact test. So we have to give the command and the Fisher exact test will be told. Another situation is the McNemar chi-square test. It is just similar to a paired t-test in the previous thing. So what does it mean? So paired observations are there. You see, I have taken two groups. One group is the smoker, another group is the non-smoker. In the smoker group, I have seen how many of them they are having ischemic heart disease, how many of them they are not having ischemic heart disease, and in non-smoker, how many of them having ischemic heart disease, how many of them having ischemic heart disease absent. So in that situation, in that way, I have created the table. Please remember, this is the only table where 64 does not indicate 64. Rather, it indicates 64 individuals, but it is having 64 into 2 observations. You see, for smoker, one response is coming, and for non-smoker is also one response is coming. So 2 persons are there in a 64. So 64 means 64 pairs basically. Am I clear? So this is the situation where we go for the McNemar chi-square test. So this is the thing, McNemar chi-square test. You see, this can be also employed. Say for example, I'm talking about this class. At the beginning of the class, I've checked how many participants they are having anxiety. Now after the class, from the same class, how many of them have anxiety? You see, in that way, I have created this table. So post-test anxiety, pre-test anxiety. So in that way, I've calculated the table. So this is the classical situation. This known as the concordant pair because before and after their category were same, and they are known as the discordant pair because their categories are different. Previously they were yes, now they are no. Previously they were no, now they are yes. So in that way we calculate, we see the this is a classical situation of doing the McNemar chi-square test, right? Now another chi-square test is left, that is known as the mental Hansel chi-square technique. You see, when the contingency table ordering of data is there, so if there is an ordering in the data sheet like in a contingency table, you see number of cigarettes smoked 0, less than 10, 10 to 20, and I have categorized the different participants in according to the presence or absence of the ischemic heart disease. So in this situation, we go for the mental Hansel chi-square test. So when there is ordering in the data set in the contingency table to see that whether there is any trend or not. These are the different names of the softwares where you can directly put your values and you can get the chi-square values by placing the cell values like this thing. Sometimes we also calculate the effect size or strength of association because all the statistical tests that we have talked till now, these are all very much sensitive to the sample size, right? So if the sample size is very small or very large, something like this thing. Sometimes we might not get and the statistical significant result, but that might not be true in in a true sense. So in those situations, we also go for the effect size. So please remember this effect size, we see the strength of association. This is insensitive of sample size. So this is the beauty of the effect size or the strength of association. So insensitive to the sample size. So whenever we see the test statistics is significant, in those situations, we go further beyond the statistical test to perform the effect size. Some of the effect size I have mentioned here, like phi, like Kramer's 5, like odds ratio, Cohen's d, eta squared, etc. So different effect size are there for different types of statistical tests. Say for example, in chi-square statistics, I have seen significant association. So next step, to see the strength of association, we will go for the Kramer's 5 test, right? So these are the situations of the applications of the effect size or the strength of association. Now let's come to the next part, is the correlation table. What is correlation? You see, I have shown you one table where you see I have categorized the different person in different weight group, and accordingly I have placed the male and female. According to the weight band, I have taken the mean systolic blood pressure of the different group. Now I see with the increase in weight, there is increase in the mean systolic blood pressure. There is also increase in the mean diastolic blood pressure, both in case of the male and both in case of the female. In these situations, we basically go for another statistics. This is known as the Pearson's correlation coefficient. Now you see, I have calculated this noted by the small r, and we also the software simultaneously also gives the p-value as well. So by Pearson's correlation coefficient, we can see the statistics. Now I'm telling you, so this is, you see, this is small r, this is known as Pearson's correlation coefficient. Now you see another situation is there. I've seen the different students of first year, second year, third year, and fourth year, and accordingly I've calculated the mean score, mean big depression inventory score. Now I see with increase in the year, there is decrease in the scores, right? So this year of the study, this is basically in ordinal scale, right? What I told you in the last class as well, nominal, ordinal. So this is an ordinal scale. So in presence of ordinal scale, we have to go for another correlation coefficient. This is known as the Spearman's rho. Now you see, I have found the Spearman rho is 0.219 and p-value is something like this thing. So please remember, whenever we are having two variables like weight and height, so two continuous variables, please remember, two continuous or two quantitative variables, and we want to see, and we basically see whether there is any relationship or not, then mostly we go for the correlation coefficient. So please remember, from correlation coefficient we get two things. One is the degree of relationship and one is the direction of relationship. What is the degree of relationship? Correlation value ranges from -1 to +1 through 0. So when it is closer to +1 or closer to -1, then we said that this degree is much higher because it is closer to 1. But simultaneously, we also see the direction of relationship. What is the direction? Sometimes we get the positive statistics, sometimes we get the negative statistics, plus or minus. What does it indicate? Plus indicates increase in one variable will also increase the other. What is negative indicates increase in one variable will decrease the other. So this is known as the positive correlation, plus sign, and the negative sign, it is known as the negative correlation. You see, this is a classical example of positive correlation. This diagram is known as the scatter diagram, where in the weight I have placed in the x-axis and the systolic blood pressure I have placed on the y-axis. And I have seen how the dots are like this. If the dots are placed like this thing, if I want to draw one straight line, you see the straight line will be look like this thing, isn't it? So this is known as the positive correlation. That means increase in weight will also cause increase in systolic blood pressure. There is also another example of positive correlation between height and systolic blood pressure. This is an example, you see, classically you see, this is an example of the negative correlation. We have plotted DAS score and we have plotted the SDL. What does it mean? Increase in dash score will decrease the HDL, or in other words, increase in HDL will decrease the dash score, right? So this is the situation where this is the QC, this is the picture will look like this thing. This is a classical picture of the negative correlation. And you see, this is another picture where you see the dots are present haphazardly in the diagram. There is absolutely no relationship with each other. So this is known as the no correlation, right? So this is a picture of scatter diagram. So in GIST, in correlation, you have to remember one correlation coefficient that is known as the Pearson's R, provided both the variables are interval or ratio scale, sorry, and both of them are normally distributed. But if one of the variable is in ordinal scale, or both in the interval or ratio scale but not normally distributed, in those situations also we go for the Spearman's correlation coefficient that is designated as rho. So Pearson's are in interval ratio scale, both of them normally distributed. Spearman's rho, ordinal scale or interval or ratio scale not normally distributed. So in those situations, Spearman's rho. This is a crude interpretation of the correlation coefficient value. So when R value is more than 0.7, we call it as a high correlation. When R value is 0.3 to 0.7, we call it as a moderate correlation. When the R value is less than 0.3, we call it as a weak correlation. But please remember, with the correlation coefficient statistics, we have to see the p-value as well. It is the p-value which will dictate whether the relationship is significant or not. Now the last part is the regression. From the correlation, we can understand whether increase in one variable will increase the other, or increase in one variable will decrease the other. But if you say for example, I have seen that increase in weight will cause increase in systolic blood pressure. But now if you ask me, sir, increase in weight in 1 kg will cause how much increase in the systolic blood pressure? That I cannot tell from the correlation coefficient. In those situations, we have to go for the regression coefficient. So please remember, correlation gives degree and direction of relationship. But in case of regression, it predicts the dependent variable on the basis of the independent variable. So please remember, in that way, two types of regression coefficient are there. One is known as the linear regression coefficient and another one is known as the logistic regression coefficient. What is linear regression? Say for example, I told you increase in weight will cause increase in systolic blood pressure. But if the dependent variable is systolic blood pressure, now you are asking me increase in weight in 1 kg will cause how much increase in the systolic blood pressure? Systolic blood pressure, it is in the quantitative form. So there is the application of linear regression. But if I change the dependent variable, systolic blood pressure, I am not keeping it as in quantitative or continuous. Rather, I am now categorized into two parts, whether hypertension present or hypertension absent. Then we will go for the logistic regression. So I'm repeating it again. When we see increase in weight will cause increase in systolic blood pressure, we can get the knowledge from the correlation coefficient. But if I am interested to know increase in weight in 1 kg will cause how much increase in the systolic blood pressure, we will go for the linear regression. But if you ask me increase in weight in 1 kg will cause how much increase in the systolic blood pressure, that is linear regression. But if somebody tells I'm no longer interested here, I'm interested to know increase in weight in 1 kg, whether will still the person will be hypertensive or normotensive, then the logistic regression will come. So dependent variable continuous, there's the linear regression, and the dependent variable I have categorized into two parts, like categorical variable, hypertension yes, hypertension absent. Then there's an example of the logistic regression. So you see, increase in weight will cause increase in systolic blood pressure. We get it from the correlation. Increase in 1 kg of weight will cause how much increase in the systolic blood pressure? We get it from the linear regression. Increase in 1 kg of weight, the person will still belong to the category hypertensive or normotensive. That we get it from the logistic regression. With this, I end today's session. Thank you very much for your patience hearing. So I'd be happy to answer your question. Thank you. Tiwari ji.
Thank you very much, sir, for very informative and session. Now, I would like to request to all participants that please write your query in the chat box or raise your hand so I can send you the unmute request. Dr. Subha, you have just wrote that how we can gain access to this software. For that, we want to inform you that there is two sessions on 29th and 30th March. There is a practical session using SPSS. On these days, you will definitely get answer of the query, then from where we install and how to use the SPSS software.
Right, sir.
If there is any query regarding today's session, then please write your query in the chat box or raise your hand so I can send you the unmute request. I'm just waiting for your queries. Thank you, Dr. Nidhi. I think all participants get answers to their queries. Uh, Thank you, Dr. Harini. For, he wrote that I feel one of the best speaker, lucid presentation. Thank you so much, ma'am. Thank you so much. I'm writing one mail ID.
So you can write down my email ID. So if you have any query, so you can write it down. So if possible, I will give you some response there over there.
Definitely, definitely.
My
Please
email
share
ID,
your
Tiwari
institutional mail ID also, and if there is any query regarding session, then mention the subject as a name of the sir or the name of the topic, so we can forward the query to the sir, and he will definitely revert you.
I've written my Gmail ID. So if you have any query, so you can ask to Amit Tiwari ji, or better you ask to Amit Tiwari ji and copy to me, and also this thing, so that all will be in a one loop. है ना तिवारी जी?
Yes, definitely, sir. Definitely, sir. Dr. Subha, you write that how to analyze ANOVA multiple Dennett's pair t-test.
So what Dr. Shubha ma'am has written is a very important question. So basically, ANOVA and PAT tests are different. ANOVA is applicable when we are having more than two groups, so three groups or more, and PAT test is only applicable for the two groups. So what I think what madam wants to know is that when ANOVA, we have done ANOVA. ANOVA is for three groups or more. Now in the ANOVA, suppose ANOVA has become statistically significant. Now the next part is to see between which two groups are different. That is why the total ANOVA has become different. That is why these are known as the different post hoc test. So Dunnett post hoc test is there. One of the post hoc tests is the Tukey's post hoc test. One is the Bonferronis post hoc test. Most commonly, we do the Bonferronis post hoc test. So I think that is the thing. So the software will give you, once your ANOVA will become statistically significant, provided you have clicked the post hoc test, then the software will give you the Bonferronis or Tukey's or Dunnett's post hoc test. Say for example, you are having four groups and ANOVA has become statistically significant. Now say for example A, B, C, D. Now probably the difference between B versus C is significant. That is why total overall ANOVA is significant. So post hoc test, Bonferronis or Dunnett's or Tukey's, they will show you, yes, it is the difference between B and C that has caused the overall significance difference in the test. I think I'm clear, Subha ma'am. So one of the participant has asked what is MANOVA. So MANOVA is multivariate analysis of variance. What I told you, ANOVA is applicable when we are having one dependent variable. When we are having one dependent variable, say for example, mean weight mean weight of section A versus mean weight of section B versus mean weight of section C. So weight is only single dependent variable. So here lies the importance of ANOVA. But what is MANOVA? MANOVA is presence of more than one dependent variable. What is that? Say for example, I am interested to see weight and height. Weight is a one dependent variable, height is another dependent variable between section A, between section B, and between section C. In this situation, MANOVA will come. I think I've been able to give you the basic difference between the ANOVA and MANOVA.
Thank you. She got the answers of their query. Thank you, ma'am. Now I think all queries are answered, and if there is any remaining query, then you can mail us on given mail IDs shared in the chat box. And
Sonia ma'am has written a query. So what is the query, Sonia ma'am?
a query, please.
Please write down the query so that we can see and we can answer.
Ma'am, please write your query. Dr. Sonia S. Kale, please, ma'am, write your query.
Or Tiwari, you can unmute ma'am also if she wants to talk.
Yes, yes, yes. Ma'am,
Yes,
please.
sir. Yeah, actually, I want to ask few things, sir. I am taking a health index of the people from WHO and Ayurvedic Swasthya Index, and this is a comparative, mutual comparative study. And whether the results which are coming out, I have to compare them. So for that, how should I proceed, and how many scales? Is there any specific guidance about number of points? Because from Ayurvedic perspective, the points are mentioned, but for allopathic investigations, I'm yet not able to decide how much number of patients will be required. So I thought, being the open platform, is it all right that I should discuss my personal study design here, or I can take your independent guidance?
Why not? Why not? It might be your personal, but the query, the clarifications or the conversation will enrich all of us now.
Yeah.
So I think in that way we can say like this thing. So what I've you told that you are having one index from WHO and another index from Ayurved, isn't it?
Yeah, and sir, from that also, Swastha and Aswastha will be two subcategories again. That is, from Ayurvedic perspective, if the person is Swastha or not. From allopathic investigations, the reports are to the mark as per requirement or not. So these ways, the four subcategories will be there. And accordingly, I have to compare. So how to proceed and how to go for the study design is my question, basically.
Basically, this is I think it is a one type of validity study. What I have understood, I might be wrong actually. So you are taking WHO perspective, and on the same time you are taking Ayurvedic Shastra perspective, and I think you want to compare between these two, isn't it? Am I correct? No,
Yes,
wrong.
the mutual comparison as well as the
Right.
individual assessment as well.
You see, ma'am, individual assessment though will not do. Basically, you have to do for the pooled analysis. Pooled. Basically, I think at the classical situations of Cohen's kappa, you go through one thing that is known as the Cohen's kappa. That is the agreement. So by one method, you are categorizing the different people. Say, for example, you have taken 200 participants. So according to 200 participants, you have categorized them as Swastha and Shusastha by WHO.
Yeah.
And the same thing, same 200
Yeah.
you have applied your Ayurved questionnaire by to categorize Shastra and Shushastra. And so in that way, this is the classical situation when we go for the Cohen's kappa agreement.
Okay.
So this is one of the things. So you write it down, Cohen's kappa.
Yes, sir.
So I think
I would like to interrupt a little because I am also planning to compare the pre-post values of the individuals as well.
So then you see this is a classical situation. What I have discussed today. If the scores are found to be normally distributed,
okay,
then unpaired student t-test. If the p-value is found to be not normally distributed, then Mann-Whitney u-test. This is the thing.
okay. Yes, sir. I'll go through it, and if
Right,
at all that
right.
query still exists, I will mail you if that's okay.
Right. Ma'am. So if you have any other question, write down, tell, or else we will close today's session.
Yeah.
Over to
Thank you,
Tiwari
sir.
ji.
Thank
Okay,
you, sir.
thank you, ma'am. Thank you, ma'am. Thank you.
Thank you, sir. Thank you. If there is any remaining query, then you can mail us. There are two mail IDs. One of sir is shared his own mail ID, and one is for institutional mail ID. You can mail us on any mail ID of your queries. write the name of that session, so we can forward that query to respective
Right,
guest speaker of the session.
right.
Thank you so much, sir, for a very informative session. Now,
Thank
on
you.
behalf of Institute of Applied Statistics, we convey our sincere thanks to all the participants for their active participation during today's session. We heartily thanks to our respected resource person of the session, Dr. Indranil Saha, sir, for a very amazing and interactive session. Our respected chairperson, Dr. S.S. Mishra, is unable to connect with us due to some technical issue. We again thanks him for trying to connect with us. And this is the end of today's session. Tomorrow we have one more session, Inferential Statistics Chapter 2, on the testing of difference parametric test delivered by Dr. Anup Kumar from GPJ Lucknow. And this is the end of today's session. We again thanks to all dignitaries and
Thank
participants
you.
present here.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you. Thank you.